The last bit, and yep. So here's a question. Who wants to hear about how to deal with news? So it's more of an applications thing. Or who wants to hear some about undirected graphical models? Okay. Undirected graphical models versus more applications. Who wants to hear about undirected graphical models? Who wants to hear about applications? It's kind of even. Okay, so what I'm going to do is I'll just show you the statistical model, but not how to solve it. So suppose we have some news stream, right? And we want to aggregate this, and we want to find out what the relevant topics are, and so on. So then, well, I can just use the recurrent Chinese restaurant process that I showed you before. It's just written up in a graphical model speak. Problem is, if I have 2 years worth of data, I don't learn anything extra, except that I get twice as many clusters. No good. After all, if I get more data, I would hope to also learn something. I can use LDA, but it's also no good because it doesn't cluster. We've tried that. It doesn't work. So you want to do clustering and topics at the same time? Well, okay. Since we're talking graphical models, I can combine both. A few more issues. You can roughly tell when those slides were made. Named entities are special, or maybe not so much. So Tiger Woods and his mistresses. And while what he did with each of the mistresses was probably similar, the names are different. So different sub-stories are essentially Tiger Woods plus X, Y, and Z. Some stories are simply strange. So in other words, they don't really follow any common word distribution very nicely. In frequent statistics at the moment, this is getting very popular under the name of dirty models. Okay, beats me why they picked that name. The other thing is that the articles sometimes deviate from the general story, so you have a hierarchical Dirichlet process. Storylines addresses this. Here's the graphical model. I'll just walk you through the model, and then we do the undirected graphical models. Okay. So if you look at this beast here, it looks a little bit like LDA and the clustering model and the time dependence all put together. So let's just look at the various components. So this is the topic model. Pretty much vanilla LDA. So here's the words distribution per topic. These are the words. These are the topics associated to it. This is like the topic distribution for a document. Okay, so that part looks very much LDA-ish. This part here is a hierarchical Dirichlet process. Basically, I'm using one to draw from the other. So that's like when you go to some restaurant and the people from that table go to another set of restaurants. This is the recurrent part for the clustering. So S is so basically what I'm doing is I'm assuming each story goes to its own cluster, and I'm assuming that each story has its own topic mix, and that the particular article that's written is then drawn with that topic mix as a prior. I get the specific topic mix for that story, for that article, and then I draw the words accordingly. And then, okay, so this is the hierarchical part again. Yeah. This bit here, well, that's because we deal with entities specially. So I'm assuming that entities are just a multinomial from a multinomial distribution. And I can sort of get away with that because there are only a few entities, maybe a dozen or so in an article. And of course, you would assume that certain named entities occur together, like Brad Pitt and Angelina Jolie will probably be, often occur together in an article. So there are clearly correlations. We entirely ignore that. Furthermore, if I know it's about Brad Pitt, I know probably what the article is about. So this is, as you can see, a crude approximation. Nonetheless, it's actually fairly decent. The other reason why we have the entities as special is because, this entire beast is now a fairly nasty intractable graphical model, and so you actually have to use sequential Monte Carlo, which I'm not going to discuss today, to do inference in. But basically, you need to have a sensible proposal distribution. turns out that a set of entities is actually a pretty good thing to latch onto in terms of a proposal distribution, and we use that. So, yep. And then here's stuff that you get. Let me go through a few slides and pick one that works well. And so suffice it to say, on TDT, we actually beat the best supervised algorithms, which is kind of cool. And here are some stories that you get. So these are the latent topics. And you can see that the entities and the non-entities are treated differently. Well, storyline here about soccer, and it basically peaks up every weekend. Tax bills, well, it's maybe less granular. And, you know, these are the people involved. And, yeah. You can do interesting things like ask, you know, what are related stories? And so you ask what are related stories, but they also need to share the word nuclear. And then you get from India, Pakistan to North Korea. Or if you just say similar by topic, you get the Middle East conflict with their own sets of names and so on. Okay, so that's reasonably useful. I'm not going to talk about detecting ideologies. Instead of that, we'll jump right into undirected graphical models. So we had all of this. Now, let's get back to chicken and egg. So suppose I don't have a temporal dependency in it, and I actually want to have chicken and egg depend on each other, right? And of course, the conditioning didn't work, right? But what we do know is that chicken and egg are, after all, correlated. We have no exact clue how they both came about at the same time. But we know that, you know, it's going to be either the chicken or the egg or whatever. So let's just encode that into some joint compatibility function. So we take some function P of C and E, and we just make it proportional to E to some psi of C and E. So that's going to get us into exponential families territory. And we know they're correlated, right? So here's what we get. We have that P of C and E is E to the psi of C and E. Now I need to normalize, namely, I need to sum over all chicken and roast chicken, egg and, well, sunny side up, of E to the psi of chicken and egg, right? And this G of psi now ensures that this all normalizes out to 1. And so I can deal with arbitrary joint distribution over, well, poultry and their products. So let's get back to our trusty Yahoo service. So we have a database and Apache. And what happened here is that, you know, as soon as I, you know, condition on maybe the website, then the database and Apache, the web server, were not independent of each other anymore. But actually what I could do is I could assume the following thing, that, you know, the site as well also affects the database, and the site also affects the web server, right? So I could make the assumption that, well, P of M, W, and A is proportional to some function phi of M and W and some other function phi of W and A. So if I do that, it actually turns out that if I condition on W, things do become independent of each other. So this is quite different from what we had before. Before, when I conditioned on the website, the things became dependent on each other. Here, when I condition on the website, the database and the web server become independent of each other, and they actually depend on each other if I don't condition on it. So this is more of an, you know, I restrict the information flow here. It's more a graph connectivity issue. So these are different representations of a joint dependence. They are not equivalent. They use a large number of similar tools, but they're not the same. And depending on your problem, you may find one or the other easier to use. In general, this type of setting gives you easier debugging. You can just sit down, draw arrows, what I think depends on what. And it implicitly defines causality. This doesn't really give you any causality, but it may sometimes give you easier modeling. Number of parameters is comparable in both cases. And a lot of the inference algorithms, basically dynamic programming, work exactly the same way. Okay. Any questions at this point? This is a rather drastic departure from what we've been doing in the past 7 hours. This difference is more powerful than it looks like. Because now if I condition on the website, these two guys actually become independent of each other. You can easily see that, right? So I just fixed W. Now all of a sudden, the function factorizes into a term in M and another one in A. Whereas here, if I do that, well, you can clearly see after I normalize properly, well, things don't work out anymore. Good. So let's pick some graphical model. So, this is now a general undirected graph. And I can ask, which variables depend on each other. So the first thing is that observing a variable here, like this one, makes the remaining components independent of each other, conditioned on that. So in general, what the recipe is as follows. You take your graph, you remove the variables that you observe from the graph and the corresponding edges, and then you have some decomposing components of the graph possibly. You need not necessarily have the separate components. For instance, if I take this variable out, the graph isn't going to disintegrate. But if they do, these disconnected components are independent of each other, conditioned on what you observe. Those two guys. I could condition on some other variables. I could condition on more than one, like I could condition on these two. And now, this part becomes independent of that part. Whereas if I take these guys, this guy here, doesn't really help me. So it turns out that if I have a set of random variables which have that type of conditional independence property. So I can start with a set of random variables defined. They need to have certain conditional independence properties. And then I ask, well, what sets of random variables, what graph and so on corresponds to it. So first of all, there's a theorem which shows that if I have these conditional independence properties, I can write them according to this undirected graph. And furthermore, if I have such a graph, it uniquely defines the set of conditional independent properties that I can have in general. So for that, I need cliques. So cliques are a maximally connected subgraphs. Who can tell me some cliques here? Okay, so the first three. Very good. Any other cliques? This one here? Yeah. This one here? Now, is this a clique? No. Very good. These two are a clique. These two are. These two are a clique. These three are a clique. Okay. Exactly, that's what we get. These are our cliques. And there's a very famous theorem, namely the Hammersley-Clifford theorem, which tells me that in this case I can write the joint distribution of random variables as a product of potential functions on cliques. That's what we have here. So P of x is the product of all cliques psi c of xc. Okay. So let me just compare a little bit more the difference between directed and undirected to give you more of an idea. Yep?
What do you mean by saying the density has full support?
Okay, so you're absolutely right. So the Hamilton-Clifford theorem says this factorization holds provided that the density has full support on that domain. Otherwise, you can construct cases where this doesn't hold.
What do you mean by that, though?
Well, it means that the density can't be 0. If it's 0 somewhere, you need to remove that instance. Good question. Any other questions? By the way, thanks for asking. I'm really happy that you guys do. Okay, let's just go through the various attributes. So in the directed graphical model, causal description is easy because I can just say, well, this guy influences that guy, and it goes in this direction, no other one. The normalization is fairly easy. I mean, the model is properly normalized as soon as you write it out. It's really intuitive. But it requires actually the knowledge of all those dependencies, and getting conditional independence is not always trivial. So you need the spaceball algorithm. On the other hand, for undirected, you only need to know the correlations between random variables. You don't really need a causal description. It's also really intuitive. Gives you a bit easier modeling. Inference can actually, in many cases, be harder. But then conditional independence is really easy to read off. Yes?
What is it that makes the inference more difficult?
Well, what makes it really difficult is that you need to normalize the distribution. So if I write out clique potentials and I have a large number of random variables, then I may not be able to compute the normalization very easily. So dynamic programming is basically a must in this context. In some cases, you can get approximate normalization and so on with message passing, but that's, not so easy. Let's look at some examples. So these were the chains from before. And I use the same plate notation, except that now I've dropped the arrows. I'm just saying, well, P of x is the product of some functions psi I of xi and xi plus 1. Okay, so if I condition on the red guy, the past and the future become independent of each other. That actually would have also happened in my directed graphical model, but that's sort of a special case. Here is a emissions model that I'm writing this way. So I might have some unobserved variables x, and I emit y, and I want to actually condition on the y's, find out what the x's look like. This will give you a conditional random field. This was one of the key insights when the CRF paper was written, that in many cases you can get away without ever normalizing properly until the end. So Leon Boutou and co-workers also had that a few years before them, and they wrote it up in such a way that virtually ensured it had to be reinvented to be made popular. So there's a beautiful paper about graph transducers that appeared in IEEE Neural Networks in 1998. And if you squint really, really hard at the paper, you can see that many of the ideas were already there, except that nobody squinted hard enough to realize it until after the fact. So it's a pretty good case in point for writing papers in such a way that everybody can read it. Yes?
Has there been much combination of them to do a directed and an undirected on the same, for example, like the time-dependent user model?
It's a very good question. Can you combine them? It's not very easy to combine them because you basically immediately lose the normalization in the undirected part. You would basically need to insert a properly normalized undirected part into the joint model. That you can do. But it's not trivial. I mean, basically, you just need to make sure that, the expressions are properly normalized. So, for instance, if you think about it, any member of the exponential family I can view it also as an undirected graphical model, and I just have my log partition function as normalization. So I can just take an undirected model and I just plug it in where otherwise I would have had some other distribution of random variables. That I can do, but yeah, kind of makes life not so much fun. So yeah, now let's just look at what we get. So here we have our chain. Yes, Leon, it's only dynamic programming, you know the stuff. So, okay. Here's what we get. We have some function, which depends. If I condition on the y's here, then I can just plug that all into some function that again now depends only on x. And I can get therefore the joint distribution over the x's by even after conditioning on the y's. I'm back in the chain. Okay. So here's the dynamic programming. This is exactly what we did before. So I just set the first message from the left to 1, constant 1. Then the I plus first message. So from the left, it's just Li of xi times fi of xi and xi plus 1. And this is now my new function of xi and xi plus 1. If I just want to get p of x given y. And so, for instance, if I have named entity tagging, this is one way to go about it. Question for you. Does it matter that there are no edges here? Could I add an edge here between the various y's? And what model would I get then? Pardon? I add more cliques. Correct. So I will add cliques between red pairs. Now if I condition on y, does it matter that I have those cliques? No, because they will give me functions that are constant, with the arguments are fixed. So that's just like multiplying it by a bunch of numbers that don't change. So I might as well leave it out. So that's why I can get away without actually explicitly writing any short or long range dependencies in the y's. The model will be identical regardless of that. So to just drive home that point, suppose we have our x's. And I want to estimate x given y. So y is, for instance, what they emit in a speech model. X might be what goes on in my mind. Now, if I have these guys, or even these longer ranging terms, or even longer ranging terms, right? And so on. It won't matter. Because I'm conditioning on all this stuff here. So what's left out, once I fix the red bits, is just the black chain. And so here's a nice Australian version for what can happen with speech recognition. So the previous Prime Minister in Australia, he was well known for not being very loving to foreigners. And he was very proud of being Australian. So at some point he talked about Australian. The speech, he wants to say Australian. The speech recognizer parsed it as so be careful what you say. So with that aside, so you might get a bit of an idea now, what you can do in a chain. But of course, chains are not the only thing you can do. Is you can do named entity tagging. You have noun phrases, verb phrases, propositions, and so on. And people have done great things with that. And so you should really look up, like for instance, Charles Sutton's PhD thesis. It has a lot of things in it. I can have trees and ontologies. So for instance, in the demos case that I showed you before, so it's due to Kai and Hoffman. So you might have, label at the top hierarchy and then so on. You walk your way down. And that now determines what the document looks like. But since you're conditioning on the document, it's actually a simple chain traversal. Just walk down the tree. And this gives you your click potentials. You can use that for ontology classification. So we did that a couple of years ago at a fairly large scale at Vichy. No, sorry. Okay, let me state the question a bit more loudly. So the question is basically, why do we have a parent here? Because we don't really have directed graphical models. Absolute perfect observation. Thanks. So this is just a parent in the tree sense. I just needed to write out the connectivity structure of the tree, but it doesn't actually mean any causal dependence anymore. Right? But basically, I just needed a way of writing, well, the guy above this node and the guy above this node. But yeah, you're absolutely right. There is no further meaning to that. Now, sorry. So can you please speak up because it's hard to understand.
What's the definition of ontology there?
Okay, so have you guys been to the Yahoo directory or Demos or basically some other hierarchy when you submit a paper, for instance, to some conference and it asks you for all the subject classifications? Then you walk down a tree of categories, and at the end, you may find something that fits, or, well, if you're unlucky, maybe not quite so much. That type of a hierarchical structure that looks like a tree is called an ontology. So in bioinformatics, there's something called the GODAG, the Gene Ontology Directed Acyclic Graph, which in a way already tells you it's not a tree anymore. It's a directed acyclic graph. That's actually a more accurate model for many things, where there are different paths how you can get to the same thing. So that's what an ontology is. Now, spin glasses and images, they're a fairly common way of dealing with, undirected graphical models. So what might happen is that you might actually, observe some pixels here, the red guys, in your camera. But underlying this might be some actual image structure, the blue bits. And those blue bits will depend on, the values of their neighbors. So, for instance, if this pixel here is black, that one's probably black too, since it's the neighbor. So there's at least a higher chance that it will be. Now, if I model stuff like that, and the most trivial model is I just, take the neighbors on top and to the right, then I get this conditional random field. Now, unfortunately, this is intractable. This classical model of what's called a spin glass. And so there you already need to do all sorts of efficient approximate inference. Talking about that would actually be probably an entire class in its own right. So yeah, we're just going to mention it and skip over it. But here's what you get if you actually use that. So Lee and Huttenlocher, so they use it for image denoising. That's the original image. These are some more trivial ones, and that's basically their Markov random field denoising, and you can see it's actually surprisingly good. Now, in some cases, you may actually not necessarily have a Markov model. So, for instance, a nice application where it's not a Markov model is when you have activity segmentation. So, what we did at some point was we looked at, well, swimmers data from the Australian Institute of Sports, and these were professional athletes. And the goal was to find out when the athletes are doing what. Now, since they are professional athletes, they behave all very professionally in the water and supposedly never fool around. But the point is basically you cannot swim and then walk at the next moment. You first need to get out of the water. And so you have constraints like that, which tell you in which sequence various actions can only occur. And furthermore, you don't quite know how long they will be doing a certain set of strokes before they switch, but you basically know that there's a certain grammar in terms of which actions can follow what, and just that the duration may be quite variable. Now, if I wanted to deal with that in a Markov model, I would require a very long range dependence. Basically, it might be, half a minute between two activity changes. If I had to do that, then I would get a graphical model that's horribly, hideously impossible to actually do an efficient calculation on. However, what I can do is I can just say, well, look, I modeled this by having sequences of variable length and then a switch between them. So you get segmentation between episodes. And the dynamic programming that you need to do is a little bit more complicated than in a simple Markov model. Actually, quite a bit more messy, but you can just work it out. You need to sit down and spend half an hour and you have it. And that gives you a semi-Markov model. You can do interesting things for web pages. That's from some people, I think, from MSR. So if you have the web page, you can decompose it into blocks. It's not a sequential document. It's the one thing that people often mistake, that if you have a web page, you don't have just text. You have text, you have all sorts of boilerplate junk on the side, you have some ads on it, and you really want to decompose it into bits and pieces. And okay, that's what they do. And it's a fairly complicated model that they use, but they seem to have gotten something useful out of it. A lot of fancy information extraction uses this style of techniques. So, for instance, you might, be able to, write a filter for 2, 3, 4, 5 main e-commerce websites. And then you use that information in a semi-supervised fashion to extract more content from other websites, where the same things are being sold, but you can't afford actually hiring a programmer to write a filter. So we might write a filter for Amazon, but maybe not one for Adorama. But since we know that Adorama sells a significantly overlapping set of products with Amazon, if I recognize, for instance, some Canon camera on Adorama, I can therefore then infer what their HTML template is. And based on the knowledge of that HTML template, I can crawl the rest of the data there. So you just go from one inference to the next, and if you have a reasonable amount of data, then you can get somewhere. There was a question here before.
Sorry, maybe it's my limited understanding, but isn't this incorporating the object model, the structure and so on for the web page?
Yes, this incorporates the structure of the web page, and if you have a good idea of what the structure should be, and you get a lot of documents that are related to that structure, you will get good accuracy.
So you're estimating the DOM basically?
Yes. So you can, so you could estimate the DOM of a web page. So I don't know exactly how they did it. I think they actually render the thing and then they pull it off. So a lot of modern web crawls crawl a page, then they render it, and then they do the document analysis from it. This gets around, stupid things like having spammy keywords written in white font on a white background. So you basically operate, or other supposedly clever tricks which do things that are supposed to trick off the search engine. Basically, you just operate directly on the content that the user sees as opposed to the content that's in the HTML. This also allows you to deal with issues like, some aspects of a page only being visible in graphics. It's not always trivial, but there are some ways how you can get around that. And it's a lot of engineering, basically. Okay. So let's just do the exponential families and graphical models again. So we saw all of this, right? That's quite familiar from yesterday. Now let's just compare conditional and unconditional models. So for the unconditional model, you have p of x given theta is e to the 5x minus theta, g of theta. And, we have all the normalization. Now for the conditional model, it's exactly the same, except that we have this additional variable x for conditioning. There we go. So you can do a conditional log likelihood. You can do a log posterior. All of that works out fine. For instance, if you want to do heteroscedastic Gaussian process regression, you could do that. You can also ignore it, make your life hard, and get the best paper mentioned at ICML for that. Happened this year. So here's the expression. Now, quite often, this expression here is expensive, unless you have a specifically simple form, like, for instance, linear and quadratic terms. And this is just your prior. So now here's the optimization problem. Let's do logistic regression. So the label space, we have phi of x and y. It's just y times phi of x. The log partition function, well, we know what it looks like. It's just, it's the log over, the term with the 1 and the term with the minus 1. It's just log 2 cosh inner product between phi of x and theta. And then I get a convex minimization problem that I can solve with any of the methods that Vichy or Manfred talked about. And it's a simple optimization problem. And then for prediction, well, I just plug it back in. And all I've done here is I've just made my life easier by dividing by that exponential term. So we get this. Yes?
Is this sort of a general rule for applying optimization problems to the exponential families of distributions? So you transfer them into their exponential form, and then you can apply these regulations?
To some extent it is. So the mapping basically goes between regularizer and the log of the prior. Those two things are closely related. They're not identical, because a regularizer just gives you an ordering, a quantitative ordering over which functions you consider simple or complicated. A prior gives you an actual distribution. So a regularizer doesn't have to be normalized. A regularizer in particular doesn't even have to be integrable. In general it is, but it doesn't have to be. Turns out a convex regularizer with minimum slopes will be, but for instance I could have a regularizer that's flat at some point. And then the integral will diverge. Okay, so here we go. That's the Hammersley-Clifford theorem now applied to feature spaces. It basically means that the clique decomposition holds in the sufficient statistics. So phi of x can be decomposed into phi c of xc. Why is this useful? Because now, when we take expectations, which we need to do for optimization, we only need to get expectations on the cliques. It also tells you what the kernel needs to look like. So who did kernel methods? Did somebody? What? Dale talked about kernels. Okay. So I hope he showed you this connection, k of x and x prime is the inner product between phi of x and phi of x prime. Now, if I plug in my sufficient statistics, so I get phi c of xc, right? If I plug these guys in, then what happens is that k of x and x prime amounts to the sum over all the cliques, kc of xc and xc prime. So, in other words, I only need to sum over the cliques. So I only need to have compatibility functions on each of those maximal cliques, and that gives me the kernel for the entire system, which also amounts to the corresponding exponential family. It's a fairly powerful connection. They need to be jointly consistent and all, but that's about it. So here's the corresponding CRF. And you just do the standard dynamic programming. So it's exactly what we had before. Now let me show you how you can do Gaussian process regression. I'll just quickly derive that for you. So remember, our sufficient statistics are, for just a Gaussian, we have phi of y being y and 1/2 y transposed. These are sufficient statistics, and so I get that, well, p of y is just exp of inner product between theta and phi of y minus g of theta. And if you plug these terms in here, you get a quadratic in the exponential. If you pick the right theta, it all integrates out, otherwise it diverges. So now a possible kernel that I could design for phi of x and y, I could, for instance, have phi of x and y to be phi of x tensor phi of y. In other words, k of x and y, x prime, y prime, is just k of x and x prime times k of y and y prime. Okay. Now, plugging this into a conditional exponential family model, in other words, if I have p of y given x and theta, that gives me exp of now a term which is basically, let's just call it theta 1 dot phi of x times y plus 1/2, and I'm just doing the scalar regression here to avoid a mess in the notation, theta 2 dot phi of x times y squared minus then some normalization g of theta given x. Okay. So what we can, if we check it, we can see that this needs to be less equal than 0. Actually, it needs to be less than 0, otherwise we have a big problem here, and the integral diverges. But it's going, if that's the case, then we have a normal distribution in y. One way to achieve this is to actually endow this phi with some offset that ensures that everything is properly normalized. Sorry. Sorry. Once I have this, and I can just have something like P of theta is proportional to e to the minus 1 over 2 sigma squared norm over theta squared, then I can just get a nice convex optimization problem in theta. It's convex and constrained. It's constrained because I need to ensure that none of the variances is negative. But it's a simple optimization problem. I get heteroscedastic regression. It's heteroscedastic because it allows you to get the variance automatically. It estimates the mean and the variance at the same time. It's a paper by Kwok Lee. Wish I had no way on the paper. Forgot who else was on the paper. ICML, I think 2000 and yeah, that's true. I think so. Yes, Stefan Canu, Lee and Smola or some permutation, ICML 2006. Yeah. So before you try something complicated, variational and non-convex, at least give that a go. Okay. I think I'm almost out of time here. It's 5 minutes questions. So I can probably, go through a few more slides, but let's just see how much. I mean, I've already done the message passing, and it's not going to change things very much. Here's just another example of, clique graph. But I think what might be a better idea is if I just take some questions, and you guys can ask me questions for the next 5 minutes. I mean, the slides are online anyway. Unless you want to hear message passing again. Okay. Yes?
How much time does it take when you fit all these graphical, especially the complicated ones, in your data set?
Oh, okay. By the way, that's the only question we have today. No, sorry. So how much time does it take to learn to solve a machine learning problem in estimation? Well, it depends. It really depends on how much data you have, how complicated your model is. So in some cases, we operate at disk speed, basically where we really care about streaming the data through as quickly as we can. In some cases, we operate below disk speed. So you can do over 1 billion documents in LDA on 1,000 machines in about a day for tracking a user for about 2 months. That's very sparse data, so it doesn't really tell you the entire story. But on the other hand, you can, with various classification algorithms, you can probably get 10 to 100 mega features reasonably easily per second per machine. It very much depends on the complexity of the model, how fast it goes. So it's basically the constraint is usually fast enough that we can use it. And within that envelope, you try to do the most complicated and sophisticated thing you can get away with. So the design constraint is usually, well, we need something that will work within maybe 50 to 100 milliseconds on the front end, maybe an hour for any user, basically for our users within a day in the back end. In some cases, you might be willing to afford a couple of days if you crawl things only on a weekly or monthly basis. So it is really highly dependent on, basically how many computers you have, what your computers are, what the hardware is. So it's impossible to tell you in the abstract how long it takes to solve a machine learning problem in Yahoo. Okay. Yep.
Which would you like to see more speed up, in the algorithms or in the computations, like the hardware? Which would be more beneficial to you?
It's a difficult question. So at the end of the day, of course, we always like our algorithms to go faster. Everybody wants that. Some cases you can do a lot of tweaking by making the model simpler. One thing that I didn't talk about at all is and it's actually a very important issue, that in some cases your state space is too big to fit into memory. So you need to do various approximations like hashing to actually squeeze things. Simple example is if I do collaborative filtering. In that context, Netflix is a tiny problem. It's a tiny problem. I mean, imagine we keep like maybe 100 attributes per user around, and we have 100 million users, right? So that gives you 10 to the 8 times 10 to the 2 times 4 bytes. You can't store that on a single machine anymore. You know, we're talking 10 to the 10, so we're talking about 40 gigabytes. Well, maybe you can do by now. I mean, you know, you can get yourself a high-end machine, 128 gigs. Maybe you can squeeze it in. So then you can deal with 100 million users. Now, if you have a service that has more than 100 million users, fun and good times. So memory is sometimes an even bigger factor, especially the access pattern into memory. So I mentioned in the beginning that you might have, you know, random access in memory that can actually really mess up things rather badly. Then you can do things like essentially cryptographic tricks or an optimal Golomb ruler to get around some of these issues. That helps. Now, in general, well, sometimes you can pre-compute things, sometimes you can approximate, sometimes you just don't run the algorithm till convergence. And there are also good statistical reasons why you may not want to do that. And Leon is going to probably talk about that a little bit. Usually what you do is if you have too much computation left over, you just make your model more complicated. So for instance, if I have a linear classifier, I could try and see how far I can get by adding quadratic terms to it. If you do that, you immediately solved the, well, too much CPU resources problem. Instead of that, you've turned the algorithm from being disk-bound into one that's CPU-bound. Or if you have a GPU in your machine, well, you can do even more fun bits. But it really depends very much on, you know, what your design constraints are. Other question? Yep.
Can you give more information for which model you will use rather than undirected graphical model and for which you use direct?
Okay. The intuition is more whichever you believe fits the model best, fits the data best, and whichever you believe you can actually implement efficiently, whichever you have an efficient solver sitting around. So there are a lot of reasons that can affect it. Sometimes it's just that you work with people who absolutely hate one or the other, so you pick one or the other one. So the good thing is that a lot of models, since they're very flexible, will fit the data fairly well. So one of the more sobering experiences was, so we did some feature selection experiments in bioinformatics. And it turned out that for some microarray data sets, basically linear and correlation coefficients were pretty much the best thing you could do. We compared like 20 different methods. That's very frustrating, right? Because people have written all those fancy papers. They've usually selected exactly the data set for which this algorithm works to go with. But in some cases, people just have different preferences for different algorithms and use them. Because they understand them better, or you have some technology already sitting around. But since models are fairly flexible, you can get away with it. Yeah, Satina.
So this is a sort of a better question. If you go back in time in AI, expert systems started with logic-based systems. Then logistic systems, graphical models.
Yeah.
And they're winning the day, so to speak. A lot of data gets used, lots of learning happens, which wasn't there in the earlier days of expert systems. How much do you credit, you think, the success to Moore's laws happen and time has passed, and just enormous amounts of data is being collected, versus the careful engineering of algorithms?
It's okay. So I think it's a matter of several things. So the area where that I probably understand a bit better than expert systems is if I look at reproducing kernel Hilbert spaces. So if you look back, there were papers in the mid-40s, early 50s, where Ronstein and so on, Reproduisante and so on, and then reprinted in the Berkeley Symposium, which had a lot of the theory in it for reproducing kernel Hilbert spaces. And the algorithms that look amazingly modern. Then in the 60s, you had algorithms like the generalized portrait algorithm by Wapnick and Lerner, and the nonlinear separation, separation by nonlinear surfaces of Mangasarian for the L1 programming. So all we actually had the nonlinear functions already in the 60s. There's the Amari paper on, neural networks backprop, and there were, a few more people who invented backprop, also from the 60s. Stochastic gradient descent proofs. So a lot of those things were available already at the time when computers weren't quite there yet. And especially for reproducing kernel Hilbert spaces, it really helps you if you can store a quadratic matrix. And then basically around the early 90s, the thing that happened is that computers got big enough that you could store maybe 1,000 by 1,000 matrix. For that you need about 4 megabytes. And that happened around the early 90s, that you could get workstations that had more than 4 megabytes of memory. So all of a sudden you could factorize matrices and you could do actually interesting linear algebra. And that gave rise to a lot of the quadratic programming, linear programming, SVM and so on, optimization algorithms. So it's not a coincidence at all that these algorithms flourished a lot, basically starting from 92 onwards. And in a way, Grace Waber just got unlucky by being, 10, 20 years too early with her ideas. Otherwise, she would have been the one who would have probably taken a lot of the credit for it. She had many, many things already earlier. It's not always clear when you listen to Grace give a talk to understand what she's done, but she actually did an amazing amount of things. So just look at her early papers. Now, what's happening at the moment is, essentially hard disks have caught up. And the hard disks are still growing at an okay rate. At least you can still grow a lot more by throwing more disks at it. The CPUs themselves have slowed down. If you think about it, when was the first time you got the 2 gigahertz laptop, and what's the speed of your laptop right now? It hasn't changed very much. So the funny thing was, like a month ago, sold my wife's laptop that was 4 years old. It was a MacBook. And I checked with the current speed of the MacBooks sold in the Apple Store, and the processor was 10% faster. Tells you something about Apple and how they manage to sell products, but it also tells you something about processors. That wouldn't have happened 10 years ago. So processors by now have really stagnated quite a bit in terms of single-core performance improvement. The multi-core performance improvement is there, and what's simply happening is that you're, successively doubling the number of cores that you're getting, so you're getting multi-core systems, but again, the increase isn't quite as rapid as it would have been otherwise. So what that means, and on top of that, the memory hasn't increased quite as rapidly anymore either. Disks have still kept up quite fast. So what that means is that now all of a sudden again, these algorithms like SVMs and so on that require quadratic amounts of memory are falling a little bit out of favor. So if you look at recent papers and where deep belief networks are starting to get all popular again? Well, part of the reason is because they are more efficient representations of nonlinear functions. You need less memory to do similar things. They are rather horrific to deal with and to keep control unless you are Jan LeCun or Geoff Hinton or Andrew Ng. But in general, a lot of people are finding it maybe not quite so easy, but often it's worth the price. Now, expert systems and general AI. Okay, I'm probably going to embarrass myself now because I don't understand it well enough to really have a good opinion on it. Moore's law definitely helped. Basically, once you are able to propagate probabilities as opposed to just binary pieces of information, you can do a lot more. Probably the biggest case in point behind the scenes that, well, we all experience, except that we usually don't know it, is turbo codes. When people switched from just, binary decoding to probabilistic decoding, where you basically decode into bits in the end and you carry through your probabilities all the way throughout, accuracy jumped significantly, and you are now able to essentially design near optimal codes without too much effort. That's also happening on your hard disk. So if you're interested in what's happening on the hard disk, search for PRML. And that's what the people in the hard disk industry basically refer to when they do probabilistic decoding of the analog signal that comes off the disk and turn it into bits. Because at the end of the day, it's stored in terms of magnetic orientations, and the orientation may be not perfect. And you can still decode things. If you convert into bits early on, you lose. The latter, of course, is cheaper, but therefore, more computation has helped. There are definitely a lot of ideas from expert systems that are probably currently right now being rediscovered. So if you are starting your PhD now, given that they are currently terribly unpopular, now might be a good time to read up on them and start publishing papers and build an industry out of it. Because they've been unpopular for long enough that very few people will know all the tricks in them. So you can republish all the ideas and claim credit for it. Happens every 10 to 20 years in academia. And not for ill will, but just because there are so many things that are being published, so they don't know about it. And people reinvent stuff. Happened to me many times. As in, I came up with something which I thought, wow, that's a great idea. And then I found out, well, 60 years ago, somebody else had that idea before me. And just nobody knew about it. Okay. Yes?
Can you comment on your last slide in terms of the last slide that you had?
This one here?
No, the last one.
Should I go further?
Yeah.
Okay, let's see. Okay, message passing, so this is just... Sorry. Yeah.
Yeah, in relation to improved method for doing estimation.
Okay, so what happens a lot in, at least when you work with real data, is, you want to find structure in the data. And you want to do that for two reasons. First of all, structure is usually good because it keeps your model simple. And in some cases, you need to also present that to humans. And as soon as you need to present that to humans, they deal with structure a lot better, with structured data rather than with just flat vectors in n-dimensional space. And in some cases, the economic interfaces are through structured data, or the interfaces in many cases are to the human. So for instance, in a search engine, well, at some point the human interacts with our products. In a spam filter, well, at some point, a user sends email. It gets filtered. Quite possibly, the user might ask, well, why on earth didn't my email go through? Nice example is if you go to Netflix and you look at the recommendations. In the recommendations, they might actually tell you, well, you like this movie because you used to like such and such a movie before. That's a nice way of giving data in a human understandable structured fashion. You may sometimes be able to get away by showing a caricature of it, but sometimes it's a good idea if your actual model then behaves similarly. Okay. So I think we probably need to take a break. I mean, time was, I think, until 10:30.
Yep.
So we're already 15 minutes over time. Unfortunately, I have to fly out, so if something happens, Vichy can probably answer all the questions that you would like to ask me, or Leon, or Carsten, or Satinder, or whoever. And yeah, worst case, just send me an email. Okay. Thanks.